Yeah.
Okay, so I'm going to be following Weinberg today. Partly there's the problem that if we use Peskin and Schroeder, they use the wrong metric. And so I'd have to change everything. The other thing is that it's a very wordy book. It's good for reading, but it's a great book. But I don't know. I just, after looking at both, I decided to go with Weinberg here. So, what I'm going to go through today is renormalization, one-loop renormalization, and I'm going to work out one that a case that is it's basically, in some ways it's the most informative because it's it involves a very divergent Feynman diagram, and but on the other hand, the Feynman diagram is not as complicated in the gamma matrix algebra and the Feynman denominators. It's not as complicated as the vertex correction, which is also a one-loop correction. So you might wonder, what are those B's? B stands for bare, and the concept here is that this is God's Lagrangian, and God's Lagrangian has fields that have infinite coefficients and infinite terms in them. And what we're going to do is we're going to write God's Lagrangian in terms of human Lagrangians, and then we'll have infinite counterterms that can cancel the divergences. So it's, if you ask me, do I like this? No, I don't like this. I've never liked anything about any procedure of renormalization. The one I like best is the one that I described in the renormalization group chapter, but how well that works for arbitrary diagrams, I'm not sure. Okay, let's look at the human field psi. This we're going to conventionally write as z2 to the minus 1/2 psi bar. I've uplifted this to the website, so it's part of class notes. It's the section 4.11, if you want to look for it. After I printed this out, I realized that I used a lowercase b for bar, but then that's confused with the Lorentz index, so I switched to capital in writing this down. Remember, I'm using Latin indices from the beginning of the alphabet to go from 0 to 3. E and finally M is an infinite mass plus an infinite correction. So that's the picture. We're going to rewrite the Lagrangian in terms of these quantities. And when we do that, then the Lagrangian is a human part. Well, it's actually a free part. So this is a trivial part, L0. L1 is the ordinary interaction. And just in ordinary terms. And then L2 is all the counterterms. So that's the picture. If somebody has mastered doing Feynman diagrams in LaTeX, please tell me how you do it. What I've been doing is basically lifting things out of the documentation for something, I forget what it's called. It has some weird name that's sort of like TIC-Z or something like that.
Yeah, that's the figure editor in LaTeX. That's what I would. That's not the best way to do it. Would just be to use that. It's obnoxious. But if you want to make them in LaTeX and not use images.
Well, all right. Look, why don't we talk about it after? If you know how to do it, tell me after class. So here we have a photon of momentum q, and going out of momentum q prime. We're going to have a fermion loop. This is going to be P. This is going to be P minus Q. And so I managed to get it to do this, but the software put in an extra arrow here, and I don't really see the point of that extra arrow, frankly. But I suppose, I don't know, I suppose it does make some sense. Anyway, this L0 is just Lagrangian of the free theory minus a quarter FAB minus Sidebar gamma ADA plus M psi. Although, frankly, I would much rather write this. I don't know why I did it the way I did it. I think it makes much more sense to write derivatives with a lower index and gamma matrices with an upper index. Just seems to make more sense to me. The interaction L1 is just minus IE AA psi bar gamma A psi. And so if we just had L0 and L1, that's what people used before they discovered counterterms and God's Lagrangian. The counterterms that we can now use to make everything finite are minus a quarter Z3 minus 1 FAB minus Z2 minus 1 psi bar gamma ADA plus M psi. So let me just write here. Let's see a couple of things I'd like to change. I notice plus Z2 delta M psi bar psi, and then minus IE Z2 minus 1 AA psi bar gamma A psi. And let me just mention something curious here, which just between you, me, and the internet, I'll mention. I don't quite understand why this works out this way. But notice that the human terms, EAA, are the same thing as the defined quantities. So in other words, the renormalization constant cancels in that. It may have something to do with gauge invariance and perhaps the idea that the charge and the gauge field belong together as one thing. But in that case, why is it that we don't need a counterterm for the quantity EA? So that's something that I should get straight, but I don't remember why that's the case. So I thought I would do this diagram in detail for you rather than just appeal to the Feynman rules, which is of course what Weinberg does, which is fine because he's Weinberg. Just for instructional purposes, I'll say that this is Q prime, S prime. It's a time-ordered product, and it's an e to the I integral L1, that's a 1, of x, and it's that acting on the state Qs. So that's the matrix element that we want to compute. And in order E squared, the correction is something I can call S2, and it's 1/2 E prime S prime, time-ordered product, and now I'll pull out the two factors of E, so we have E squared integral AA of x psi bar x gamma A psi x equal x integral AB of x psi bar, I'm sorry, y gamma B psi y equals y QS. So that's what we've got to deal with. And now, of course, the electromagnetic field, let us say AB of y is an integral d cubed p over 2 pi cubed to P0 sum S prime, or really S double prime, e to the I Py EB of P S double, I'm using S double prime to avoid the S and S prime in the initial and final states. A of P S double prime plus e to the minus I Py E star B E S double prime A dagger P S double prime, and I guess that's, well, we have a trailing right bracket there. Okay, so that's that, and now what we want to do is we want to substitute the electromagnetic field in these two places. Now, as usual, this 2 is the 1/2 factorial from the expansion of the exponential. And over here, what we're going to do is we can choose either AB of y to annihilate the incoming photon, or we can choose to have AA of X annihilate the incoming photon. So those are two choices. They give rise to the same number, the same complex number. And so what we can do is we can say, well, we'll forget about that. We'll use that factor of 2 to cancel the 1/2, and we'll just choose to use to have the electromagnetic field at point Y annihilate the incoming photon, and have the electromagnetic field at X create the outgoing photon. And if we do that, then S2, taking into account all these factors here, is E squared EA star of Q prime S prime EB of Q and S, and we have 2 of these square roots, so that just gives us 2 pi cubed 2 Q0. The Q comes from the fact that A of P and S prime acting on the state Q and S gives us a delta of P minus Q and a delta of SS double prime. And so that gives us this factor here and a Q0 there. Then we're going to have an e to the I. P has to be Q, so this is e to the I QY. Right. And moreover, we're creating the photon, outgoing photon at X, so that's an e to the minus I Q prime X. And so we have these factors here, e to the minus I Q prime X plus I QY. What's left inside the time-ordered product is, well, we have just vacuum time-ordered product, quadratic expression in Fermi fields, another quadratic expression in Fermi fields, and then the vacuum. And, okay, I've just gotten ahead of myself here, so I noticed I skipped something in the notes. So let me just leave it this way, 0. Okay. Time-ordered product, and the integration's already started. What's left here is Sidebar of X, gamma A, psi of X, Sidebar of Y, gamma B, psi of Y, close the time-ordered product, and of course we have d4 of X, d4 of Y. Right, okay. All right, so this is the expression. Now, what I've been a little bit sloppy, and I guess Weinberg's been a little bit sloppy also, or maybe he just said that the normal ordering is implicit. So the interaction Lagrangian is supposed to be normal ordered, or normally ordered, which means annihilation operators to the right of creation operators. That's so we don't have particles, positrons created at Y and then absorbed at Y, which actually I think would give a divergent integral, the same thing at X. So for this reason, the particles created by psi of Y have to be absorbed by psi bar of X, and particles created by psi bar of Y have to be absorbed by psi of X. And so what we can do is, the nice way to deal with this is to take this psi bar and move it through these various terms to get it here. And if we do that, we wind up with 1, 2, 3 minus signs, and that extra minus sign is the minus sign that Feynman mentioned a long time ago when he said if you have a closed fermion loop, you have a minus sign. So let's see. So if we do that, well, let's see. I did this in my notes in 2 steps. So let me put in the 2 steps. This part is the same in both steps. So we can say this is also equal to ditto plus, and then here we have, well, ditto there, and the change here is 0 time-ordered product of psi bar alpha of x, gamma A alpha beta, psi delta of y, and then I put in vacuum states here, another time ordering, psi beta of x, psi bar gamma of y, and gamma beta sub gamma delta. And I'll just put a ditto there. So the idea here was, first of all, this psi bar gamma A psi, gamma A is a 4x4 matrix, so I'm using Greek to label 1 to 4. So, but then I took this psi beta of x and put it over there and moved the psi delta of y forward, and let's just check that there's no minus sign in this case. So we move this across 2 fermion fields to here, and then so that's just a plus sign. And now what we do is we move this psi delta of y forward to there, and that gives us our final minus sign. So the amplitude S2 is now minus E squared EA star of Q prime S prime EB of Q and S 2 pi cubed 2Q0 integral E to the minus I Q prime X E to the I Q Y. And now 0 time-ordered product of psi delta of y, gamma, well actually I was writing that what I wrote was correct, psi bar alpha of x, and then gamma A alpha beta. And then that's multiplied by 0 time-ordered product psi beta of x, psi bar gamma of y, and then there's the gamma beta, gamma delta. And one might as well put brackets there, actually. let the gamma matrices just sort of hang in free space there.
Kevin, can I ask a question?
Yeah, you can even get it. Oh, I did it wrong. I need to erase that. Let me just finish.
Yeah, sure.
All right, what was the question?
Yeah. Oh, actually, you didn't. You still need a cat, right? Yeah. No, I guess you weren't done. Anyway, the point is I was wondering. So what we're doing here is we're just doing this kind of like Wick contraction, right? Like using Wick's theorem to break up all of these this time-ordered product of 4 things into time-ordered products of pairs of things. What about the sidebar x psi x term? Do you not have this term?
Oh, well, the idea is that everything's normally ordered, so we don't need to worry. The most that happens is a minus sign when you move one past the other.
No, I'm saying okay. We have this. We turn this time-ordered product of 4 operators into a product of these vacuum expectation values of 2 operators, right? But isn't the idea that we're supposed to sum over all possible combinations of pairs of operators that we could pick? Isn't that the idea behind this Wick theorem?
Well, frankly, I find the Wick theorem to be, I mean, it's great that Wick did it, but I think it's more instructive for students just to see how it works directly. I mean, you don't need Wick's theorem, which is for arbitrary diagrams and arbitrary.
It's arbitrary vacuum expectation values of time-ordered products of operators. But I mean, okay. So then why in this case do I not have a term that would be like sidebar x psi x? Why is there no term that's like sidebar x psi x, like vacuum expectation value sidebar x psi x?
Well, because that would be 0, because
Okay.
it's normally ordered.
Because it's normally ordered.
Yeah.
Okay. And
Yeah, you'll overcount by 3 terms if you don't have normal ordering, right?
So the normal ordering avoids that kind of thing.
Sure.
And I think Weinberg says maybe 100 pages before chapter 11, he, I think, mentions that he'll normal order everything. And people often show normal ordering by having a colon. Then you'd have to have colons, you know, in so many different places, it gets tiresome. All right, now, we derived back last semester what this time-ordered product is. The time-ordered product of, well, I'll use the notation that I used. And I'll just use the part that we're actually going to use. Minus I d4 q over 2 pi to the 4th. Or in fact, we're going to use p or k. So let me call it k. Minus I k slash plus m lm over q squared plus m squared minus I epsilon e to the I q x minus, and it's k. I decided to switch because we have q in this thing, so we're going to use k. So that's the fermion propagator. And now what we do is we just take this and use it, substitute it in for the 2 vacuum mean values. In fact, this would, actually I need to rewrite this. This is actually, like that, and then gamma B, gamma delta. And in fact, this one also would look nicer if we wrote it that way. So that's what we've got to deal with, and if we substitute that in, then what we get here is S2 is equal to E squared E star A of Q prime and S prime EB of Q and S 2 pi cubed 2Q0 integral e to the minus I Q prime dot X e to the I Q dot Y integral d fourth K 2 pi to the fourth minus I K slash plus M, and it's delta alpha because it's delta alpha here, so that's delta alpha over K squared plus M squared minus I epsilon e to the I K, and notice it's YX, and so it's Y minus X, and then gamma A alpha beta, and then the same thing, but use P as an integration variable. So we have d fourth P, 2 pi to the fourth, minus I P slash plus M beta gamma e to the I P X minus Y, and now P squared plus M squared minus I epsilon. And then we have a gamma B, gamma delta, and then finally d fourth X, d fourth Y. Now, if you see these for the first time, what you might think is that this is just hopeless. It's a 16-dimensional integral over, and all the integrations go from minus infinity to plus infinity. So this is hopeless, but of course, once again, Dirac saves us with his delta functions. And so what I do when I get something like this is I just write this down as x times, and it's minus q prime minus k plus p. And we're integrating over k, so that means that this goes to delta of k minus p minus q prime. Or I see I put in an unnecessary sequence of minus signs. Let me just write it as p minus k minus q prime. So that tells us that that the p integration is equal to k plus q prime. And so this turns out to be, I'm sorry, P is not the very, it's K that, it's K that I want to get rid of and not P. So this says that K is equal to P minus Q prime. So we say K equal to P minus Q prime. And then the coefficients of Y are Q plus K minus P. But K is already P minus Q prime. So this is Q plus P minus Q prime minus P. So this is Y times Q minus Q prime. So that's an overall delta function of Q minus Q prime. So altogether, what we're left with here is S2 is equal to E squared EA star of Q prime S prime EB of Q and S delta fourth of Q minus Q prime over 2 pi Q, 2Q0. By the way, this delta function that Dirac is using to rescue us, maybe I'll write it down over here just in case some of you don't remember what it is. It's integral d fourth k over 2 pi to the fourth e to the I, e to the plus or minus I, k dot whatever, let us say W, is equal to delta 4 of W. So back here, what we're left with is an integral d fourth p. Notice we had a 2 pi to the fourth here and another one there, so the 2 pi to the fourths are gone. We just have d fourth p, and then we have minus I p slash minus q slash. That's because k is equal to p minus q prime, but q prime is q. So k turns into p minus q plus m delta alpha gamma a alpha beta minus I p slash plus m beta gamma gamma b gamma delta, and the denominators are p minus q squared plus m squared minus I epsilon, and over here p squared plus m squared minus I epsilon. So these are look like that. Okay. All right, so this is where we are at this point. And by the way, in case somebody hasn't seen this notation, this is A sub A gamma A. This is Feynman slash notation. In LaTeX, the thing is backslash, slashed, curly bracket, whatever, curly. Okay, so what do we have now? Well, what we have is a trace, because you see this is a sum over alpha, beta, gamma, and delta, and this is a matrix where m is multiplied by the 4x4 identity matrix. So this is a matrix product, delta alpha, alpha beta, beta gamma, gamma delta, summed over all of them, that's a trace. So this thing is equal to, let me just say the same thing, integral d fourth p, trace of minus I p slash minus q slash plus m gamma a minus I, let me get the signs right, p slash plus m gamma b. So that's the numerator, the trace, which is just that trace. And then the denominator is the product of p minus q squared plus m squared minus I epsilon times p p squared plus m squared minus I. So that's what we've got to evaluate with this prefactor. Now, the traces, as you know, are very nice things algebraically. Trace of AB is trace of BA, which follows from a more general result. Trace A, B, dot, 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 Z is trace of Z, A, B, Y. Okay. And so the trace is cyclic. And if we also interchange A and B, then what we get is that S2 is E squared E. So I'm interchanging A and B, and I might as well set Q equal to Q prime. EB star and I'm going to set S equal to S prime. I think that comes about automatically. Delta fourth of Q minus Q prime over again 2 pi cubed 2Q0. And what's left now is D fourth P trace of minus I P slash plus M gamma A minus I P slash minus Q slash plus M gamma B, and it's all this over these propagators, P squared plus M squared minus I epsilon P minus Q squared plus M squared minus I epsilon. Okay, so that's that, and let me, I hate writing this over and over again, but I guess I must. So Weinberg extracts from this the following definition: P star AB of Q, and it's basically everything apart from the delta function in this overall factor here. And so it's minus I E squared over, and he puts in an extra 2 pi. 2 pi to the fourth, D fourth P, and it's this trace of, again, minus I P slash plus M, gamma A, minus I P slash minus Q slash plus M, gamma B, and then P squared plus M squared minus I epsilon times P minus Q squared plus M squared minus I epsilon. This is, by the way, the first time in this course where the minus I epsilons actually matter. And now we want to use a Feynman trick, and I may assign this derivation of this integral as a homework problem, but it's elementary. Okay, this is one of Feynman's many, many tricks. Another of his tricks was cracking safes, and of course he did that at Los Alamos. Embarrassingly, security people. Okay, so what's the use of this? Well, you see, here we have a product. So we have an integral that's 1 over a product of two quantities. If we can write that as an integral over an auxiliary parameter x, then we can arrange to have something involving a sum of these quantities, and then we can do something q. And in particular, we're going to write this denominator 1 over p squared plus m squared minus I epsilon times 1 over p minus q squared plus m squared minus I epsilon. I'm going to write that as an integral 0 to 1 dx over something squared. And I'm just checking how many parentheses I need here. I see, I don't think I need so many parentheses. So let me just put a notation there. Let's just say this is then p squared plus m squared minus I epsilon times 1 minus x plus, oh, I do need the extra thing, damn it. P minus q squared plus m squared minus I epsilon x, all of that squared. So that's the trick. Now if you expand these things, you see that in fact it is integral 0 to 1 dx, and this denominator then is p squared plus m squared minus I epsilon, and then minus 2 p dot q times x plus q squared x, all of that squared. So what's happening here is that the minus x times p squared cancels the x times p squared, and there are other cancellations. And now these things can be combined so that we have 0 to 1 dx over p minus xq squared plus m squared minus I epsilon plus x 1 minus x q squared, and all that squared. Okay, so that's what happens after the Feynman tricks. Now let me get a better piece of chalk and go on with this. Anybody ask a question and not get a candy? Anybody starving? Anybody else starving?
Yeah, sure.
Maybe more accurate.
This is left hand. Yeah. Okay, now, so far we've ignored the fact that this is a badly divergent integral. In fact, it's quadratically divergent. And what's really going on, of course, is that the physics at very short distances is stuff that we don't understand. This physics at very short distances obviously makes everything finite, because we're talking about elementary particles, so everything is not only finite, but tiny. So consequently, there's something going on that makes everything quite finite, and so what we're going to imagine now is that we have some way of, well, first of all, we're going to write this in this way, but we're also going to imagine that we've made the integral finite by some regularization process. The process of making integrals finite that in quantum field theory, that is, has been most widely accepted in the last 40 years or so is something called dimensional regularization. The advantage of dimensional regularization is that it doesn't interfere with Lorentz invariance or gauge invariance. Another advantage of it is that it's very slick, and it just sweeps away all kinds of things in just an instant, and poof, everything's finite. And then one can then deal with things. So I'm going to imagine that we've made this integral finite by dimensional regularization. Dimensional regularization basically means that instead of integrating over d4th p, we're going to be integrating over we're going to let this parameter 4 become a complex number. So the number of dimensions is going to be a complex number. We're going to let that then be a variable that when it's not 4, but is, let us say, 2, this whole thing is finite, and then as we go from 2 to 4, we see these infinities pop up again, but then at that point, then we bring down the counterterms and cancel them. So that's basically the procedure here. So at this point, before we, so if we imagine, all right, so so I don't have to rewrite all of this yet again. Let's imagine that we've rewritten the product of denominators this way. Once we do that, then obviously a shift of p goes to p plus xq simplifies the denominator. It makes, of course, the trace more complicated, but the trace is in the numerator, and so that's an easy thing to cope with. So, if we then imagine that we've regularized this integral, use Feynman's trick to write the product of denominators as this integral here, and then shift p goes to p plus xq, what we get is pi star AP. The star here does not mean complex conjugate. The star there means that we are considering, it's actually a notation that we don't need at this point, but literally it means that we're considering the second order. Well, let me not tell you what it means. At another time I'll tell you what it means. At the moment, let's just call it, let's just say it's not complex conjugation. So this is minus I e squared over 2 pi to the 4th, integral 0 to 1 dx, integral d4 p. And after the shift, the trace is a little more complicated. Namely, it's minus I p slash plus x q slash plus m gamma a. So let me just write some brackets here. And then minus I p slash minus 1 minus x q slash plus m gamma B. And now this denominator, which is simplified, and it is p squared plus m squared minus I epsilon plus x 1 minus x q squared squared. Okay, so that's what we have to deal with. But notice we've got this crazy trace in the numerator. Now, we discussed traces last semester, and in fact in section 4.8. So these are the online class notes. These are the trace identities. If you just look at those trace identities, you can then apply them to that trace there. And what you find is that the trace, and I won't write it again, I'll just write what the answer is. As you know, traces tend to be 4 or 0, and the coefficient of 4 is minus I p plus x cubed a p minus 1 minus x q b. I'm going to write this a little differently from the way Weinberg writes it. P plus x q b p minus 1 minus x q a, and then plus p plus x cubed dotted into p minus 1 minus x cubed a to ab. I think that's in fact it. I rewrote things slightly, but that's actually what it is. Okay, so that's what the trace identities give you. So now,
is this superscript A and B, is that a component of a 4 vector, or?
Give me that again.
What is the superscript A and B?
What's the what?
So you have like p plus x q to the b.
You mean A to AB?
No, not A to AB, the other terms. Whenever you have like those terms above, where you have like p plus x times q a.
P plus x q a.
Yeah. What is the a denoting there?
The a is a Lorentz index.
Oh, okay. So you're saying consider the 4 vector
P plus x q a.
Oh, okay. Sure. Fine. Yeah.
But you burned your candy.
And so it's, yeah.
And they can vary 1 through 4 again, right? We're using the Greek to vary 1 through 4.
Somebody else wants candy. All right, hold on here. All right, what did you say?
Because over here we have alpha, or through here alpha, beta, delta, and gamma are varying 1 through 4, right?
Right.
And are A and B varying?
A and B are the A and B that are associated with the original gamma matrices. They also go from 0 to 3 at this point. But once you trace them out, they're gone. And actually, that question that you ask is quite a good question, because the A on gamma A is a Lorentz index going from 0 to 3, and these A's are Lorentz indices going from 0 to 3 on P and Q. Now, so this is what we've got to deal with. We have this integral, and we substitute the numerator. For the numerator, we substitute that. Okay, but at this point, we do something called a Wick rotation. And I once met Wick, by the way, a long time ago. Anyway, what's the Wick rotation? Well, you see, we've still got the I epsilons here. Moreover, this p squared is p vector squared minus p0 squared. So these are two awkward things. One is that as we integrate p0, it's going to hit p vector squared at some point. We're going to get a 0 there, or we're going to get something negative that can cancel over here. So altogether, this is an awkward integration for that reason. And in fact, that's the reason we have the I minus I epsilons in order to regularize that. Well, it turns out that the nice thing to do is to say, well, in the P0 plane, let's imagine that P0 is a complex number for the moment instead. So initially, this integral says, if you want, you can consider P0 to be a complex number, but so far in this integral, you're just integrating from minus infinity to plus infinity on the real axis. Okay. On the other hand, there is a pole here, and there's another pole there. So, if instead of having P0 be real, we added a contour up here, then, now, what about that contour? That contour is what I called, in the complex variable course, I called a ghost contour. What we imagine is that we've regularized this integral sufficiently that it's not only finite, but as we go out in the p-plane, this contour is a ghost contour. Then we can rotate, instead of integrating from minus infinity to plus infinity, we can go from minus I infinity to plus I infinity. And that makes the integral a much nicer integration, much nicer integral. So in other words, we're now going to be integrating from P0 equal to minus I infinity to P0 equal to I infinity. And we're going to set P0 equal to minus I P4, or equivalently, P4 equal to I P0. So here, so the new variable in the integration is going to be P4. P4, though, when P0 is plus infinity, P4 is plus I infinity. And when P0 is minus infinity, P4 is minus I infinity. So this is a much nicer integration here, and we're going to have dP0. All right, I screwed up here somehow. Let me just get this right. P4.
I think you've changed around the superscripts.
Yeah, I've screwed things. What I want to say is this is plus I. P0 is I P4, so when P4 is plus infinity, P0 is up there. All right, that makes more sense. So then P4 is minus I P0. Okay, I've now got the notation scrambled because my notes are the opposite of what I want to say. And right, well, for sure we want to rotate the contour, and we want P0 and P4 to be related by an I. And well, certainly dp0 is going to be I dp4, right? Because dp4 is going to be going from minus infinity to plus infinity. So that means P0 goes from minus infinity to plus infinity. So P0 is I P4, I think, is the right way to think about this, right?
I mean, geometrically that makes sense.
So and that means P4 is minus I P0. So when we do that, we get an extra factor of I that turns this into +1, where we have P squared, which is P vector squared minus P0 squared. This is now P vector squared plus P4 squared, or it's just Pi squared summed I equals 1 to 4. So this is, we're now in effectively Euclidean space, a Euclidean momentum space. And for example, if we have something that's P0, P0, eta 0, 0, and let me use the convention that I've now decided is correct. P0 is I P4. But I think Weinberg has the opposite convention. So this is I P4 squared times minus 1. And so this is just P4 squared. And we can fix this to P4, P4, delta 4, 4. So in other words, we go from Minkowski 4 vectors and eta, we go to Euclidean 4 vectors and just a Kronecker delta. And we then have pi star AB of Q equal to 4e squared over 2 pi to the 4th. Integral 0 to 1 dx. Integral. Now d4 p is Euclidean p. So maybe I should put an e there. And what we have is minus p plus x cubed a p minus 1 minus x cubed b minus the same thing with AB interchange, so p plus x cubed b, p minus 1 minus x cubed a, and then plus p plus x cubed dotted into p minus 1 minus x cubed. And now delta AB. And this whole thing is then divided by p squared plus m squared plus x 1 minus x q squared. Okay, so so this is the integral we have to deal with, and we imagine that all along we have regularized this integration. And so the next steps are dimensional regularization. I haven't regularized, I haven't latex this part, so I'm just going to use this technique. It was introduced, by the way, by Hooft and Veltman back in, as long ago as 1972, which means that it's almost 50 years old now. And the idea, of course, is what we've got is we've got a denominator in which P is rotationally symmetric. This has O4 symmetry. Okay, it's just P1 squared plus P2 squared plus P3 squared plus P4 squared. And up here, these P's are all just suitable P, the same business. They're just all real. And so basically what we expect is if we have a P1 times a P2 in the numerator and we integrate, that's going to be 0. On the other hand, a P1 squared will give something that's non-zero. And so what happens is PA, PB is going to turn into P squared eta AB, or delta AB, divided by D, where D is the dimensionality of this integration. I'll do this again on next, today is what? Wednesday. Next Monday I'll do this again. We only have well, we're out of time now. Let us just say that this, well, I'll explain the whole thing on Monday in more detail.
Whose pen is this?
That's mine.
I don't know if Peskin and Schroeder do a longer discussion. I don't know if it's any clearer than one word. But it's just a way of making things finite. Okay, you go. Do you need a candle?
Turn this off. Okay.
Yeah, turn it off.